Okay, so we're just going to run through my philosophy for teaching, the philosophy behind this class. And yeah, so what I'm actually going to do is have you go back to the back and we don't even need very many. So just grab, we're going to help you. We're going to get some supplies, and you guys can do this together. So you just need one set of supplies. So you need that and this. Fill this halfway with water. You need a hunk of clay, a candle, and a lighter. Yep.
So the videos that you post are just a little demonstration on how the lab works?
Did you get the link for the first one?
Yeah, I did.
Okay, yeah, so I actually just ran through kind of the lab safety issues with the lab,
Okay.
and then I demonstrate how to do the lab, and I'm going to demonstrate what things you should cover lecture-wise. So, yeah, and it's pieced together because I did one a couple years ago, but I didn't do any calculations on the board, so it kind of jumps around, but hopefully you get. But if you read, and I've written very detailed instructor guides that even have things like, students might think this, and this is wrong because, so why don't you pause here? And so it's got a lot of teaching tips in it that should help you. But if you're at all worried about it, you can always attend someone else's lab and just sit in the back and watch them do it. I used to do that when I was a TA. Okay, perfect. So take your candle, make a ball with your clay, stick your candle in the clay, and stick it to the bottom of that dish in the middle. Okay, now you're going to light it. All right, and then you're going to take your jar and just place it over top. Okay. And just observe how much empty it is. We'll see if it works. Okay. Did you observe anything cool?
So the candle went out.
Okay.
And then
Let's
once
try
it
again.
went out,
I usually use glass in much better. I use glass. Just move the jar onto this. All right. Try it again. Okay, anything, observations? All right. So give me your observations. What did you notice? Candle went out, right?
candle went out. The jar became cloudy, smoky.
Okay.
Once the candle went out.
Okay, and the water rose. All right. Do you have any burning questions in your mind?
Why the water went out?
Causing a vacuum.
All right. So why did the candle go out? Okay, do you agree with that?
Yes.
Okay. Why did the jar get smoky? Because there's smoke.
From the burning wick.
Okay. There's fire in
It's a
there.
combustion reaction.
All right. Why did the water rise?
It's a vacuum.
Why?
There's some pressure change.
Yes. Why? Talk to your neighbor for a second.
So
See if you can figure it out
in a
together.
combustion
the two of
reaction,
you.
oxygen is converted into carbon dioxide. But carbon dioxide is heavier
and putting on my teaching hat, I would be walking around to other tables. What do you guys think? What do you guys think? Okay, because you're having to talk to the neighbors. So I'm gonna sort of put teacher hat on.
Oh, so carbon dioxide dissolves,
Well, I guess oxygen is too, carbon dioxide.
30 times more though.
more.
Carbon dioxide is
Okay.
30 times more soluble than oxygen.
Okay, so it dissolves in the water.
It's less in the atmosphere and it pulls the water up.
Yeah.
You've got an explanation? Okay, tell me. Put it into a nice succinct.
CO2 is better dissolved.
So you're saying O2 is changing to CO2.
Yep, and then the CO2 is dissolved in the water. So there's less atmosphere in the jar, and so there's less pressure, so it pulls the water up.
Okay,
To maintain.
other ideas? That's a good explanation, but it may not be the right one.
Dr. Jensen can do magic.
Magic, I will take that. What else? Now, obviously, if you have more
Maybe-
groups, we're gonna get more ideas, right?
Maybe some type of air pocket in the clay and, I don't know.
How's that working for you? How does that work? Oh, where the air is going into the clay? Making less air in the jar vacuum?
Yeah, it's more soluble in clay than in the water. So.
Okay, so maybe the CO2 air is dissolving into the clay. Okay, what else? So what I noticed that didn't go up, because you automatically said oxygen changed into CO2. But often, one of the answers students give is that the oxygen is just gone. Right? The oxygen disappeared, left it after the jar. Okay? Yeah, you guys said it's turning into CO2, so maybe there's not something gone. The CO2 is going into the water. What else? I'll give you one. What if the fire wants oxygen a lot, right? What if it's trying to pull it from the water? Or what if it's a heat thing? It's just getting hot and then cooling.
Also, the air time is hot, so it's less.
Yeah.
So,
I'm just throwing ideas out here. We got magic already. That's
We
good.
wanted to do the opposite though.
How so?
Because
It would make it
because
expand.
temperature and pressure are directly related. So if you increase the temperature, then there's increased pressure in here, which will push the water away.
So then when the chemical's out though, could it be that it cools?
The opposite.
Maybe, I don't know if that's fast enough, but. Okay. Okay, let me pause for a second and put on my teacher hat. Couple of things. So all these labs start with some kind of puzzling phenomenon. All right, that gets them kind of started into the process. And it's important that you don't tell them the answer. And it's important, one of the tips I just used was when I ask you a question, if everybody's just staring at you, like, you have no idea. So I'll say, okay, tell me, what's the first law of thermodynamics? And everyone just looks at you. Or what's your hypothesis? Then you say, okay, turn to your neighbor and tell them, and then we'll talk about it. Because students are happy to tell their neighbor all their crazy, weird ideas. They won't say it out loud. Right? And I'll do that in lecture all the time if I ask a question and everyone's like, I'll say, okay, talk to your neighbor. And then when you get back as a class and say, okay, did anybody come up with a good idea? Often they do. But still, sometimes you'll have it where they still don't want to share their idea out loud. And so then I say, who would like to share their neighbor's idea? Everybody wants to share their neighbor's idea. So getting ways to get students talking is a really good one. The other thing that I do all the time is I'm not ever standing up in the front of the classroom for a long time. Right? I'm walking around so that everybody feels like they're equally on the spot than just the one table you're next to. So you want to be walking around. Anytime you give them a problem to solve, you want to be walking around and make sure you visit every one of the 8 tables. So you need to sort of be quick, and you feel like, oh my gosh, I'm having the same conversation 8 times. I should just have it as a class. No. have the same conversation 8 times. And in your case, in lecture, we're gonna have the same conversation like 30 times. But with individual groups, because when you're talking to just individual people, they're much more likely to ask you questions if they don't understand than if you do it with a friend. So we're gonna give them problems to solve in class, and then we're gonna walk around and talk to every little partnership. And be like, what do you think? What do you think? And have the same conversation over and over again. But it's the better way to teach. All right, so going back to here, we've got these things on the board. Let's go back and look at them for a second. So now I'm back to teacher, your students. We're back in the student mode. Well, if you would name those, what would you name those? That the candle went out, that the water went out. What are those?
Observations.
Good, they're observations. So these are observations. And I like to call them puzzling observations. And I wish they put the words slower in these words. Puzzling observations, because if they weren't puzzling, nobody would go anywhere with them, right? We'd just quit. So, puzzling observations. This we call a causal question. It's the reason we do science, right? We want to know why. What are these? Okay. So you know the scientific lingo. These are hypotheses. What is a hypothesis? So that's what we always think, an educated guess. But based on what you wrote up here, what is a hypothesis? That's a prediction. We'll get to that in a minute. But what is this in relation to what we've written up here? Yeah, it's an answer to the causal question. A hypothesis is a potential explanation for some phenomenon. Now everybody says, oh, it's an educated guess, but I don't think they really understand what that is. It's actually an answer to the question, why did that happen? Why does that look that way? Why did this evolve this way? Hypothesis is an answer to a causal question. All right, I would write that down. So you have students write it down. Now notice that, so I'm going to back on my teacher hat. I don't introduce any terms. That one's where yeah, I don't just say, by the way, this is called, this is backwards teaching. It's constructivist teaching. So I could have given a PowerPoint and been like, a hypothesis is, a puzzling observation is, this is the scientific method, but instead, you did it, and then I labeled it for you. So all these labs and all the lecture stuff, we're gonna, now lecture, sometimes I have to get into lecture mode because there are certain things you can't discover very easily, molecules and stuff. But we try to always get them thinking and giving a possible explanation. You say, you're right, this is what it's called, or you're sort of right, let me modify that for you. But if you get the students to give it to you before you give it to them, they're gonna know it. If you give it to them, it's gonna go one ear, not the other. So the goal of all these labs is to get them to come up with the answers. And you're walking around with groups and you're helping them come to the answer. You're not telling them anything. And they're gonna get sometimes frustrated with you, like, can you just tell me the answer? And the answer is no. I can't. Because if I tell you the answer, you won't know it. You need to discover it on your own. And these labs are all set up for discovery. Okay? So even like gel electrophoresis, we're gonna give them a setup and say, how would you use that? How is this even gonna work? And they're gonna not have a clue. They're like, I don't know. Well, what do you know about DNA? Well, I know it's got a phosphate. What is the phosphate? It's phosphate. It's charged. So let's say DNA is charged, which it is. How's that gonna help you? Maybe it'll go towards one of the poles. Okay, so if it's going towards one of the poles, and we've got this crazy meshwork of the gel, what do you think is gonna happen? Oh, well, it's gonna get sort of hung up. Yeah, it is. So do you think longer or shorter pieces are gonna go faster? You see, like, instead of just telling them, this is the gel, this is how it's like, this is how it runs, you want them to think about, oh, because logically it all makes sense. You just never would have come up with it on your own, right? Smart people invent these things. But it's all logical, so you can help students get to it. Okay? All right, so we've got hypotheses. Your job is to figure out which one is right. Okay, and I've got back in the back different size jars, additional candles, syringes with tubing, baking soda if you want to carbonate the water. Like if you wanted to test number 1, you could saturate the water with carbon dioxide. Anyway, just okay. So go ahead. Just take just a couple minutes if you can figure out what is the right answer. If you want to mark the level of the jar, the whiteboard markers work really well. Okay.
Well,
And I'm just going to pause this.
No, I don't think so. Unless you have like one of
So I'm gonna
those
pause you
things
for a
that
second
have
because they're
temperature
testing
counts.
stuff.